Hi, everyone. I'm Dale Kim. I'm the Senior Director of Technical Solutions at Hazelcast, and I'm very happy to talk about our platform with all of you. So as a quick agenda, we will talk about what is Hazelcast, how it's used, how it fits into your existing infrastructure, how is it different, and then I'll discuss a few example use cases. So this is a quick elevator pitch of what Hazelcast is. And we'll go through each of these components as part of this presentation. But think of Hazelcast as simply an open source, Java-based data platform or application platform where you can build the fastest applications in environments where high throughput and low latency are extremely critical. And so performance is obviously a big part of our deployments, but also in cases where you want to do more work in less time is where it can be critical as well. And I'll give an example of where that applies. So I mentioned open source, so I want to clarify some of the differences between our commercial enterprise edition versus our open source. So with our open source, you get all the core components, you get the high performance, the high availability, so the replication within a cluster to make sure that if a node goes down, that you don't suffer any data loss or any downtime. The out-of-the-box connectors to the many different data platforms that we integrate with. We do limit the monitoring of a Hazelcast cluster to some extent on the open source version, and we provide community support. And so in the enterprise edition, it's all about trying to simplify your production deployments. So whether you have a mission critical environment, whether you have high speed transaction-based environment, we want to simplify it with a lot of these features that you probably need, like security, like higher scale. So this higher memory per server aspect is what we call our high density memory store. And if you think about Java frameworks where you oftentimes will face a garbage collection pause as a result of taking up too much memory from the Java heap. We've built a module that allows you to go up to 100 gigabytes, and we're going to be extending that further per server without the garbage collection pauses. So that's written in native code and allows you to allocate much more memory as part of your in-memory deployment and without any of the impact of the garbage collection that you see in Java. There are features around disaster recovery, so WAN replication, automatic failover. There are also some features like rolling upgrades and blue-green deployment support that helps to reduce the planned downtime. The monitoring capabilities are unlimited, and of course, professional support as part of the Enterprise Edition. So this is a good metaphor for what we do. So we are a data platform. It integrates with your existing infrastructure, and it's about making your applications run faster. So if this is a before and after picture, on the left, you have a fast car, a great driver, and a good-looking car at that. And for the most part, it seems to work well. But what if you got that extra boost? What if you supercharged it? Would that give you an opportunity to win more? And in many cases with our customers, that's absolutely true. And so one thing that's interesting about this is that we didn't replace the car. We didn't replace the driver. We added something on. And so, as you add a supercharger to your car, you can't exactly drive the same exact way. So there's a little bit of adjustment that you have to make. And same with us. When we integrate into your system, you might be writing to a database for reads and writes and any types of aggregations. And so you will have to modify your applications a little bit, but that will help you take advantage of the in-memory and the streaming capabilities that we provide within our platform. And let me talk a little bit about the architecture when it comes to distributed computing. So most of us are familiar with a database cluster. So on the left, databases are mostly for storage, not entirely, but mostly you think about it. So if you're looking at petabytes of data that you want to store as a system of record, you would use a clustered database system. And the applications would typically run on a separate node. So the application node is where the work is being done. The application will do a request, send off a request, get some data back, do some processing, save that data. And it's very intensive on the application side, and the database nodes are mostly about managing the data. Now contrast that to our foundational roots in our architecture, where we were started off as an in-memory data grid. And so the data grid is about moving code closer to the data. And so what's happening on the right is that you submit code, and so the application code is actually running on the cluster nodes next to the data that resides in memory. And so you get this divide and conquer type of methodology that parallelizes a lot of the work takes advantage of local data, processes local data before combining it all together. And what that means is that you're not only taking advantage of the CPU power of all the nodes in your cluster, but you're also reducing the network traffic of moving data. And so if you think about some of these big data environments where you could potentially be moving tons of data before you can process it, that's going to impact your network, and it's going to impact your overall performance. And by submitting the code and sending it off to this distributed computing cluster, then you can take advantage of all the resources that you have within that cluster acting on data locally. So that's one of the big differences in how we're architected versus some of the more common models pertaining to databases. I also want to talk about some of the data flows within Hazelcast. And so on the left, we have streams or streaming data or event streams. So any environment where there's an incoming continuous feed of data, which could be from machines, it could be from enterprise applications or IoT devices, anything that's creating data on the fly that you want to respond to quickly, that you want to analyze and identify patterns. That's where Hazelcast can fit in. And so after you do some type of processing, then you send it off to some other destination. So that's the streams portion. And there's another data flow that deals with ad hoc requests, commonly known as the request response paradigm, where a user or an application will submit a request. Hazelcast will get that request, do some type of processing, generally using data from a system of record, and then give an answer. And so if you simplify this to its basics, a cache is a perfect example of that, where you might just be moving data from your original source, storing it in memory, and just delivering to end user application. And so it's just a fast way of delivering that data, especially if there are repeated data access patterns. But where Hazelcast fits in is that we're more like an application server in that middle versus a cache, where a lot of processing can be done to create that answer. So it's not only passing data through, but doing some type of processing, enrichment, aggregation, filtering to give an answer. And so I intentionally oriented these horizontally and vertically to line up with our diagram here, and you'll see the streams going horizontally, and then there's the ad hoc requests going vertically. And so within the Hazelcast platform, we have the two components of streaming and in-memory that you saw in the earlier elevator pitch slide. So at the bottom where it says distributed memory first database, you can think of it as a storage mechanism in memory. Because it's distributed, it handles all of the fault tolerance capabilities to make sure that there is no data loss. There is some notion of persistence so that you can ensure that there is extra durability should a node go down and you want to restart quickly. And then above that is the processing layer. So you can use Hazelcast for streaming data, but also in batch data. If you think about it, streaming data is unbounded incoming continuous feed of data, and batch is simply a bounded stream of data. So you can use that engine for processing data and then sending it off to the next destination. And we have the application tier at the top. So we have an API for which you can build your applications. Microservices has been really popular with us because of the lightweight nature of our platform and the ability to build these very specialized, purpose-built microservices that can communicate with each other through Hazelcast. And so we support a number of languages: Java, C++, Go, JavaScript, Python. And so you can build your applications that access the high performance aspects of our system. And I mentioned earlier about how we integrate with existing systems. So we're not about replacing your systems of record or replacing your databases. We want to tie in with the data that you already have. And that's been an important strategy for us because a lot of companies we talk to have legacy systems that just would not make sense for them to overhaul. I mean, if you look at a lot of these companies at big industries like telco, healthcare, financial services, they have sometimes mainframes or very old relational databases that have been built many years ago. They work well. They might be expensive, they may not be the most modern, but we can tie in and take advantage of that data to deploy new channels, new applications, and not have to have them mess around with your existing system. So now I want to talk about the individual components as part of this overall architecture. So I talked a little bit about the core platform. So, we view ourselves as, if we can view ourselves as the center of the universe in terms of the different parts of the ecosystem. Let's take a closer look at some of the other components. And so I talked about this part, the data source, as being the input from streams or even batch processing. And so you'll see the different types of sources we might have. Typically, these might be data sources that create the data. So it might be an IoT device or an enterprise application, or it might even come from our own in-memory store. Or it might be a repository that's good for holding streaming data, like Kafka or any of the messaging queues out there. And so a device might write to Kafka, store that long history of streams, and then we can read from that. And the advantage of using Kafka in this environment is you can replay that stream from Kafka and be able to index or process the data in a different way. And so having that flexibility of being able to repeat work on the same amount, on the same data is a great advantage in event-driven architectures. And so we have a number of out-of-the-box connectors that can allow you to integrate quickly with a lot of these interfaces so that you get the data coming in. A lot of times it's transactional data, and we use our engine for processing that data, doing all types of transformations, and even delivering data to a built-in machine learning inference capability. So as you're getting, say, purchase data, you can send it to a machine learning model, get a score, and then pass it on to the next stage in the process. And this is the sync side. So typically in an event-driven architecture, after you're doing some processing, you'll deliver to something else. And so many cases you might read from, say, Kafka, a specific Kafka topic, and then write to another specific Kafka topic. So that's certainly one of the important paradigms for stream processing. But you can also deliver to a number of other locations as well. And another popular technique is getting streaming information, indexing it, and formulating it in a way that it's ideal for end user analytics, and then dumping into some analytics repository, whether it's a data warehouse or RDBMS, or even into our own memory store. And then from there, end users can run drill down analytics on that data. And because it's prepared for that type of drill down, it'll be really fast. And at the top, I mentioned some of the programming languages that we support. And this, again, is the endpoint into our system for that request response type of paradigm. So you have these microservices that can act, or you can have web and mobile applications that can be built. And a lot of our customers are moving into that area where they want to build out a lot of their channels for customer interactivity. And if you think about it, with a lot of their legacy systems they have in place, a lot of the activities that a user would run within the application are not revenue generating. So you don't want to spend a lot of money trying to serve account information to a customer, especially if the backend is a mainframe. And that's where building out a wide variety of newer channels and using Hazelcast as that middle data platform is really effective. And then we have reference data, RDBMSs, data warehouses, data lakes. So anywhere where you store your master copy of data, and it could be spread across many different repositories, we can read that in and use that as reference data. Let me just quickly talk about.
Dale, yeah, so a question about the data ingest from systems of record.
Yeah.
Are you a caching layer into those systems as systems of record? That, is it a continuous updating of data that you maintain a second copy of? Are you like a thin cache where you fetch on demand? How does that ingest work?
Yeah, absolutely. So because we have a compute layer built into our system, we can have that continual update. And there are a number of ways that you can do that. One of the more popular ways today, or the emerging ways, is using CDC. So if there's any updates to those systems of record from an external application, we can tap into the transaction log file, see the updates, and reflect that into our system.
Okay, so I end up with a parallel. How do you cross-check that with the system of record to make sure that it applies in the same way?
Yeah, there's write-through mechanisms that you can include as part of our platform, so that any updates that are being done directly from an application into our platform will be reflected into the system of record.
Okay, so it's a kind of like a write-through cache. Okay.
Yeah. And so, like I mentioned, that's one of the simpler use cases. But when there are responses that are required, that requires a lot more computation, like calling out to a machine learning algorithm, that's where we really shine. All the additional processing that you can do instead of just the straight pass-through of data.
Okay, and you mentioned that you have support for different languages for front-end queries. Presumably, that's a very different way of querying because you're an in-memory grid system, which is mostly about mappings.
Yeah,
as
exactly.
So the way that I'm querying data from existing systems.
Yeah, I'm glad you mentioned that. So we do have our own API for querying, and we have a very SQL-like predicate system for querying against specific field elements. We also support SQL, so you can use that as a mechanism for querying within both the streaming data.
I was expecting it to be more like a MapReduce type functional mappings query. But
yeah, you can use the API for something similar to that. So similar to a MapReduce methodology.
Okay.
And so I'll go over this quickly, but some of the key architectural principles, we have a lot of information on this slide, but I just want to touch on cloud first. So all of the promise of the cloud, the agility, the elasticity, safeguarding against instance failure we provide. We support the different cloud vendors as well as the different platform as a service technologies like OpenShift, Kubernetes, VMware Tanzu. Memory first is a nod to our in-memory roots where, as you know, in-memory means all the data is in memory and none of it spilled over to disk. And we've extended that so that memory is the primary access point for the purposes of speed, but also for durability, we persist to disk. We claim to be fast and reliable, and so we've put a lot of effort into making sure both of those components are top tier priorities. Because if your system is as fast as possible, but relaxes reliability, and we're aware of at least one other technology that does relax reliability at higher speeds, then you don't really get credit for being fast. It's like having an extremely fast car that blows up when it goes 150 miles an hour. And so we make sure that the data is protected, that replication continues, that we have the disaster recovery capabilities in place, regardless of the workload, and we just optimize for speed to make sure that we can keep up.
Do you have any additional information or just some numbers on latency metrics around certain operations?
Yeah, I'll talk about that.
Okay, cool.
Yeah, I have a benchmark slide, so I'm happy to cover that some more. And so another aspect that we want to cover is just the simplification of the entire architecture. So our software package is self-contained, it's very lightweight, it uses a familiar object-based API. You can embed it in applications, so you can link your applications to our library, deploy that application across a number of nodes. They'll broadcast to each other if you configure it that way, and they'll recognize each other as a cluster. And so that's an alternate deployment mechanism versus client server. And that's ideal for certain purpose-built environments. It's ideal for the edge. And so the simplicity of the development has certainly been a key thing for a lot of our customers, where they want to add new capabilities, but they didn't necessarily want to overhaul everything or add a lot of time to their effort. And quickly, how is Hazelcast different? We're familiar with databases, storage focused, some compute capabilities. They're oftentimes considered heavyweight. We know about stream processing engines. A lot of them are designed for real time, but really aren't that fast. They really aren't designed for the extremely low latency environments. And then we traditionally, many years ago, competed in the data grid market. So when I talked about the code being distributed across all the different nodes and processing all the nodes, that's what a data grid is. And that's the big difference between databases. And so what we try to do is combine the best of all worlds by having that integration of the in-memory storage, the distributed computing, and the stream processing. And then all the other architectural principles that we include help as an advantage as well. And so obviously, if you look at this, then where do we fall short versus some of these other technologies? And really what it comes down to is the large storage. So if you're looking at huge petabytes of data, if you want that system of record of all your historical data, you're obviously going to turn to a database. And of course, that's where it fits in with us relying on systems of record, and we become the processing layer, the fast processing layer, working with those databases. Let me talk about traditional architectures and a different way and how we're different. So at the top, you have a stream processing engine, oftentimes a lot of complexity in deploying across a cluster of nodes. And in any streaming environment, because the data tends to be pretty sparse, you oftentimes have to enrich it with reference data, and you get that reference data from your systems of record. But you need an external data store as that intermediary as for the purposes of enrichment. You don't want to access your system of record directly. So in a streaming environment, in an event-driven architecture, you have the stream processing engine and an external data store. These are separate technologies, but you need them both together. And these are both necessities in any streaming environment. And so what people face is not only the complexity of tying these two otherwise complex systems together, but also the latency associated with reaching across the network and hitting an otherwise disk-based database as the external store. And so where our advantage lies is in the integration of these two components. And so we have one package, one server system that has both the stream processing and in-memory computing packaged together. So as each of the tasks in a stream processing job are running, they will have a copy of local data in which they can do the enrichment. And as more processing goes on, there are some other optimizations that we run in terms of near caching and so on that will help improve the performance. And so here's some numbers around our performance. So any technology that claims high speed is going to want to look at the billion events or billion records per second type of achievement. So we use the Nextmark benchmark suite, which is a benchmark created by Portland State University that simulates an online auction. And it creates bids and various actions, includes a series of questions about the different states of the different auctions. And so we wanted to see, what were the characteristics of the hardware if we wanted to get 1 million events per second being fed through our system. And so we defined a 20 millisecond window, meaning that we're running aggregations every 20 milliseconds of data input. And we experienced 16 millisecond latency at the 99.99th percentile. So very low latency for almost all of the data that we're processing. And this was done on a C5 4X large instance on AWS. So it's a 16 virtual CPU system. And so overall, 20 nodes, 320 cores is what we got for that 1 million events per second. And so if you look in the upper right, that represents the readings for the latency at various cluster sizes. And that query at the top was a query that asked which of the auctions had the highest price for this last time period. So it had to check what were the prices, how it compared against previous prices. So a lot of complicated processing there, and hence it was the slowest among the we tested. So we used that query to see how much hardware it would take to get 1 billion events per second. And so we changed the parameters so that it's a little bit more realistic. We used a 500 millisecond tumbling window, and we experienced 26 millisecond latency at the 99th percentile, 99th percentile being a more standard readout for latency in these types of benchmarks. And we did in only 720 cores in AWS. We experienced that near linear scale. And so at the low end, we get about 25 million events per second, but at the 45 nodes, we're getting 1 billion. And if you compare that to other technologies out there, generally require several thousand, maybe 2,000 or more, a couple thousand cores to be able to handle performance like that. So this is not only about the speed that we have, but also the efficiency. So if we're very efficient at all levels throughout the scale, that means you could potentially run on fewer clusters, and that certainly helps out with the simplicity and the low overhead that you can get from us.
Dale, for clarification, is this a standardized benchmark test? I mean,
yes, it is non-vendor specific.
Does this bleed across your industry, or is this something that is that you guys would like to focus on?
I think our engineers found it because it's an emerging benchmark. So it was created at Portland State University. So that it was created independent of us. So they had created it, and we decided to pick it as one benchmark to use for streaming.
Thank you.
So I talked about performance, and a lot of times we think about performance as a means of doing a given job in less time. And this is one of our customers, a card issuing bank, which saw a different opportunity by having additional performance headroom. And so if you think about card swipes, most of the time that you wait after you're swiping or tapping your card is for the information to be delivered over the network, which means that you really don't have a lot of time for the processing. And so this customer said that they were still getting a lot of fraud on their transactions. So if they could cut down the fraud by creating a more accurate fraud detection system, they could potentially save millions of dollars, if not more. And what they saw with Hazelcast is that instead of running one complex fraud detection algorithm, they essentially had a competition among their data scientists to run multiple fraud detection algorithms at the same time. And they came up with a composite score that represented a better, more accurate indicator of fraud. And so, of course, fraud detection is an estimate. It's a prediction. It's not an absolute. And so you can always try to get better. And by having this composite score, they were able to improve the accuracy, not only from the standpoint of identifying fraud, but also reducing false positives. And if you think about a false positive, it's saying that your transaction is fraudulent, even though it isn't. But if you're a consumer, you're just going to use a different card. And so this bank will lose out on that transaction fee. So they want to reduce the number of false positives as well. And so by running these all in parallel, Hazelcast gave them the performance advantage to be able to do that. And so they were cutting down on over $1 billion in fraud purchases, which was saving them tens of millions of dollars, maybe closer to $100 million per year as a result of better fraud detection.
Dale, you mentioned on one of the previous slides that you're using Optane, Intel's Optane, as a way of, in some mechanism. How are you using Optane? Because it has two modes from memory.
Yeah, exactly. So one is, I think the really interesting part for us is the volatile memory mode. So as an alternative to DRAM, where you can have larger scale per server. And so now you have these bigger, beefier servers with more memory, more data stored in memory, faster access times, fewer servers, so lesser network traffic as a result of working with that. So certainly there was some work that we did on our side to optimize to use the Optane API. And then on the recovery side, so if you think about populating an in-memory store, reading, all the data generally comes from some other source like the system of record, and being able to repopulate the in-memory store after a shutdown or after a crash requires a bit of time. So what if you can just read that prepped data directly from disk? And that's part of our persistent memory or our persistence story. And so we were seeing 2.5 times faster recovery times by using Optane as a fast SSD versus some of the traditional storage media.
Sorry, but again, correct me if I'm wrong, but I thought that you could either use Optane in one mode or the other, but not both simultaneously. So
that is correct.
Like cheaper DRAM or it's persistent.
Yeah, so those are two separate use cases. So in one case,
so you have some in one mode and some in a different mode for different use cases.
Exactly.
Okay.
And the form factors for Optane of those different, I believe, are different. So DIMMs for the volatile RAM, and then more SSD form factor for the other.
Okay.
I have a question about kind of the customer deployment models that you see. I mean, clearly this is, it's software can be deployed anywhere. Do a majority of your customers, are they running on kind of the public cloud providers versus, running within standard, their enterprise constructs or their private clouds? Do you see kind of a differentiation, one that's more prevalent than the other?
Definitely still more prevalent on on-premises deployments. So certainly there's a lot of interest in cloud, and we're growing. This particular customer for this card swipe is in the cloud, but we're still seeing a good majority on premises.
Dale, I didn't understand how you manage the node failures or other disruptive events. I mean, is there a copy of the cache on other of this grid on other nodes? So how do you distribute data to?
Yeah, we have a replication mechanism that most distributed systems have, so that we can create what we call backups, but it's a copy of each of the data onto the other nodes. So should any node fail, then the system will recognize the failure, and then it'll redistribute the data to optimize it, considering that there's fewer hardware resources. And then once that node comes back up, then the data will be redistributed again to be able to take advantage of the full powered cluster.
And what is the impact in case I lose a node? I mean, for all this rebalancing and distribution on the application?
Yeah, we've done a lot of work in terms of optimizing the rebalancing. So in I forgot the numbers, but like if you're looking at like a 2 terabyte, I think, cluster with about 20 nodes, then it might take about 33 seconds to rebalance. So it's pretty quick in terms of recovering should a node fail, and then it should be pretty fast as well when you add the node back in.
Okay, thank you.
So yeah, the rebalance is all about the optimization. It's not about shutting down. So it's all the applications will still be running nearly full power. You just have to accommodate the load and the memory usage so that if a node does fail, then you're not at 100% memory on all your nodes. So just some pre-planning there required.
Okay, I got it.
So this is the Swiss Federal Railways, and their acronym is actually SBB CFF FFS, which represents the German, French, and Italian names all combined together, but I'll refer to them as SBB for short. But one of their issues is just being able to schedule trains, which is a well-known, well-studied, but very complex mathematical problem, and it's very time-consuming and error-prone when done manually. And so obviously using computers are a great way of being able to speed that up. And they want to run these scheduling programs very much like a real-time analytics environment, where you don't kick off a job and then come back a few minutes later or after lunch and then look at the results and try to decide what's a better route. And with all the complexities, it does take time, but how can they squeeze out every last ounce of performance from their system? And that's where they turn to us. And if you think about all the computations that are being done, they have information on how long tracks are, or how long trains are, how long of a train each station can take, where the trains are going, all the timetables of who needs to go from where. And so with all that complicated information and the overlap between the different routes, there's a lot of math going on in the background. And one of the bottlenecks is retrieving data. So they used Hazelcast as a means of storing all of that system of record information in Hazelcast and doing the computations with very fast reads and writes from within us. And what they've developed looks like a simple cache, but what the advantage is some of the other opportunities that they have as a result of starting off by simply storing data. And so this is the notion of a digital integration hub, which I would say is like a supercharged cache where you have the compute available within the cluster. And so now with all the data within their Hazelcast deployment, there are some other types of computations they could be doing in the future, and maybe even adding stream processing as another component for any real-time updates that might be going on. So if there is some disastrous event, or like a train stalls or something, and they get that information, can they recalculate some routes? And that's part of the advantage of where they can use Hazelcast for additional types of capabilities like that.